Alright, this is Algebra 2, Chapter 7, Section 5, Exponential and Logarithmic Equations. So, in the past, we've been solving exponential equations by sort of finding a common base, and then when you find that common base, then we can solve for x. But that's not always usually the case because x might not always have a common base. So what happens when you don't have a common base? What does that answer look like? So we'll attempt to solve those questions here. So here they got an example of a problem that you guys have done that's very similar to what you've done in the past. And they have here that 27 to the 3x is equal to 81. We're going to rename both 81 and 27 to the x. And we're going to say that 27 is the same thing as 3 to the third power. And that's being raised to the 3x. Likewise, we're going to say that 81 is 3 to the fourth. We multiply the 3 and the 3x, so we get 3 to the 9x is equal to 3 to the 4. At this point, we don't have to worry about the bases, and we can say 9x is equal to 4. Divide both sides by 9, x is equal to 4 ninths. Now, we've done that before. But what happens when we can't find a common base? What does that look like? How would we solve that type of problem? Well, we can solve it by either raising it to the 10 or raising it to, or using logarithms. And so we have a similar type of problem. 5 to the 2x is equal to 130. In this particular case, there is no perfect base. There is no 5 raised to some power that equals to 130. That doesn't exist. So, in this case, we will use logarithm. And we're going to log both sides. So we're going to log 5x, or 5 to the 2x. And we're going to log 130. Using our properties of logs, the 2x is going to drop to the front. And we're going to have 2x times log of 5 is equal to log of 130. All right, we're going to divide both sides by 2 and divide both sides by log of 5. So x is equal to log of 130 over log of 2. Oh, I'm sorry, log of 5 times 2. Okay. So log of 130 divided by 2 times log of 5. And that gives me that x is equal to 1.51. Yeah. Let's raise both sides, or log both sides when you have an exponential equation. The 2x is going to drop in front, and then we can divide both logarithms and solve for x that way. Again, we are doing this because the bases, we can't get a common base. There is no 5 to some number that equals 130. And since that's not the case, we can use log. We can also solve these things by graphing. So they have method 1 and method 2. I'm not going to even look at method 2. I'm going to look at method 1. And what happens with method 1 is if I wanted to do a solution of this guy by graphing, 7 to the 4x equals 800. I'm going to break this up into two different graphs. The first graph is going to be 7 to the 4x, and I'm going to graph that curve. It looks something like that. And then we'll say that equals y. And then we're going to have a second one, y sub 1. And that be 800 is equal to a y sub 2. So this is a horizontal line. So you're going to have an exponential growth curve like this. You're going to have some horizontal line, and their intersection is the solution. All right, their intersection is the solution. So when I do that, I have y equals 7x right here, and that says y equals 800. So let's go looking for 800. 800. It's a big. So you have y equals 800 right here. So here's the horizontal line, y equals 800. Here's our other one, y equals 7 to the 4x. You look for their intersection, and that's not the intersection. I mean, it is the intersection, but there. There it is. That's weird. Yeah, the intersection is at 0.859. Right, so that's the intersection of 800 and y equals 7x, 4x, or 7 raised to the 4x. Then they give us another one. They give us this guy. And again, we'll separate up into two equations. Y sub 1 is equal to 5.2 raised to 3x, and y sub 2 is equal to 400. And where they intersect, and again, this is another exponential growth. Where they intersect is going to be the solution. All right, so here we go here. Here we go here. So this is 400, so let's make that smaller. Here's that intersection. Right, and it's going to be at 1.211. Okay. So that's one way of doing solutions with graphing. Of course, graphing will take forever. It would be better just to use logarithm. Okay, so that's that. All right, here we can use logarithm with exponential growth models and decay models. So remember in the past we learned using the inflation model for putting your money to a bank and deposits, and how much would it grow over time. And it would be like a to the n equals like the principal times 1 plus the interest rate raised to the n power, something like that, or some initial. I forget the actual equation, but it's to the point. We're going to utilize the same equation to solve this. So we have 1,200 trees. 1,200? 1.2 million trees. We want to know how long it would take if this is a foresting company. How many years it would take if we took 5%, down here. If we took 5% So our rate is going to be 5%. So in decimal form, that's 0.05. 5% of the tree every year. We cut it down. How long would it take to have half the trees used? Well, half of 1.2 million is 600,000. So how long would it take for you to get 600,000 trees at a rate of decline of 5%? So we would say that not only would it be 0.5 cents, but it would be negative 0.5% because it's a decrease of percentage. So the equation that the book gives for this problem is T of n, T for trees, equals A, the principal or the initial, times B sub n. All right, in this case, B is equal to 1 plus R. So that's where that's coming from. So when we plug in all the numbers, it's going to be 600,000 equals the initial amount of trees, which is A. So this is A. And this is T of n. 1,200, not 1,200, 1.2 million times 1 minus 0.05 raised to the n, and that's that n that we're looking for. Divide both sides by 1.2 million, so 600,000 divided by 1,200,000 racks. And that equals, we're going to do subtraction here, that's 0.95 to the n, and we're going to log both sides. We're going to do the math here, that's 1/2, so 0.5, so we're going to have a log of 0.5 equal log of 0.95 raised to the n. And remember, when we raise something to the n and we log it, that n is going to drop up front. Sorry, n drops up front. And when the n drops up front, we're going to have a log 0.5 equals n log 0.95. Divide both sides by log 95, and we get that n is equal to log 0.5 divided by log 0.95. That's going to get us the number of years. We do that, and we get it would take them 13 years, approximately 13.5 years to cut down half of the trees. It's a damn shame. That's a lot of trees. It's a lot of trees. Yeah. All right, so solving this guy, when we have an equation that has log in it, we can raise it to its opposite. So log of 3 minus 2x equals -1. Here's the thing. Since there's a log already involved, we can get rid of that log by raising it to its inverse. So 10, remember, we're at 10 to the log is equal to 1. Right? Remember that log is at base 10 here, so these guys cancel out. So what I can do for this is I can raise both of these guys to the 10. 10 to the log. So in this case, it's going to be 10 to the log 3 minus 2x equals 10 to the negative 1. These guys cancel, and I'm left with whatever is being logged. So that's going to be 3 minus 2x is equal, 10 to the negative 1 is 1 over 10. Right. 1 over 10, I can also make it a decimal and say 0.110. I'm going to subtract 3 from both sides, so negative 2x is equal to negative 2.9. Divide both sides by negative 2. X equals 1.45. Or I can graph it. That's method 2. And I do their intersection. So I would have for my y sub 1, y sub 1 would be log of 3 minus 2x, and then y sub 2 would equal y equals negative 1. Alright, plug those bad boys in. Whoa. Here we go. There's that graph right here. And then y equals negative 1. They intersect right there. And guess what? I get the same number. 1.45. Hallelujah. Alright. Okay, so using log to solve problems. Again, same thing. Here we have log of 6 minus log of 3x, and that equals negative 2. First thing I'm going to do is combine these and turn it into one logarithm. So if it's subtraction, then I have division. So this is going to be log of 6 divided by 3x is equal to negative 2. Once I do that, I'm going to raise both sides to the 10. So 10 to the log of 6 over 3x and 10 to the negative 2 on the other side. And remember, log and base 10 log cancels out, so I'll have 6 over 3x over here. I'll do this into a fraction, so this is the same thing as saying 1 over 10 to the second power, which is 1 over 100. So I'll write this as 1 over 100. And guess what, y'all? I can cross multiply. So I get 3x is equal to 600, and x is equal to 200. Would you look at that? All right. I want to actually go through the problem here in the book too, because it has quadratic properties. So for this one, they have log of x minus 3 plus log of x, and that equals 1. So you have two adding of logs, so we can multiply x times x minus 3, and this would be log of x minus 3, and that would be multiplied by x, and that equals 1. Again, I can raise both sides to the 10. So this is going to be 10 to to the log of x minus 3 times x, and that's going to equal 10 to the 1, which is just 10. These two go bye-bye. I'm left with, and I'm going to distribute that, so I have x squared minus 3x equals 10. Alright, so I have the makings of a quadratic. I'm going to subtract 10 from both sides, and I have x squared minus 3x minus 10, and that equals to 0. So two numbers that multiply to negative 10, it adds up to negative 3. So x minus 5 times x plus 2. So I have two potential answers. Either my answer is 2 or my answer is 5. And you have to check these because since it's a quadratic, you can have extraneous solutions. So I plug in 2 and I plug in 5, and the book does the math. It works for 5, does not work, or I'm sorry, for negative 2. So since it doesn't work for negative 2, it only works for positive 5, x equals 5. Alright, that is that section. I hope you have a great rest of your day.